Hi everybody, Justin here from chemistrynotes.com, and we are continuing with section 18. Section 18 is called Transition Metals and Coordination Chemistry. So this is video number 2, and in the first video we discussed the importance of transition metals. We also discussed some general properties of transition metals. Video number 1 was, for the most part, a review, and this video will also be essentially a review of transition metals. In video number 3, we'll start talking about coordination chemistry and complex ions and ligands and all the different types of complexes that you can have with coordination compounds. So, top of page 1 of today's notes, and remember, when I bring up a topic like electron configurations or oxidation numbers, I'm focused on transition metals, right? The D block elements. So electron configurations, we covered this extensively in section 7. If you can review that now if you'd like. And we don't have to use the diagonal rule when assigning electron configurations, but here it is in case you want to reflect back on how to use it. Just follow the arrows, right? 1s2, 2s2, 2p6, 3s2. Now, there are 2 notable exceptions that I want to mention to the diagonal rule. And those are chromium with 24 electrons and copper with 29 electrons. According to the diagonal rule, you would get what's listed there, and then what's crossed out is replaced with the way it really is. So chromium, instead of ending at 4s2 3d4, is 4s1 3d5. Okay, beneficial to have all of those 5 d orbitals half filled. Copper, 29 electrons. Instead of ending at 4s2 3d9, it's 4s1 3d10. Those aren't the only exceptions, like silver is another common exception, but those are the 2 I wanted to put in our notes. All right, when drawing electron configurations for ions, electrons are removed from the 4s orbital first, not the 3d orbital. Now remember, because I'm talking about transition metals, our ions are going to be cations. They're going to be positively charged. Okay, so copper plus 1 as an example. That would mean 28 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. I put a box around that answer. I removed the 4s1 electron. All right, so that's electron configurations. Just wanted to touch base on that. It's something we've covered already way back in section 7 in the first semester of general chemistry. All right, the next topic for review for transition metals is oxidation states. Oxidation state is also referred to as oxidation number. And for the most part, a metal is going to take the same oxidation state as the charge it's carrying at that time. So it says most metals have more than one oxidation state. They also have multiple charges, right? Most transition metals anyway have multiple charges, so they can have more than one oxidation state. And these 2 numbers are usually the same. For example, Fe can be a 2 plus or a 3 plus. Those are also the oxidation states for iron. Okay, chromium likes to be, it can be a bunch of other things, but it likes to be 3 plus and 6 plus. Those are also common oxidation numbers. Copper plus 1, copper plus 2 is another one, right? Tin plus 2 versus tin plus 4, right? Tin is Sn, if you remember. So that's oxidation states very quickly. The next one is ionization energy, and then I want to talk about atomic radius or atomic size. Those are the last 2 I want to talk about. So ionization energy trends. Okay, well, if you remember back in section 7, I kind of drew a rectangle, and if that were the periodic table, then ionization energy would increase from bottom left to top right. Okay. So the ionization energy is the energy required to remove an electron from an atom. In other words, my M metal atom plus energy, that energy is used to remove the electron, leaving me with a metal ion product. If this is my periodic table down here on the bottom left of this page of notes, then ionization energy increases up a group. It also increases left to right across the periodic table. Okay? And there's nothing new there. That's just the trend for how easy or how difficult it is to pluck off or remove an electron from a metal atom. All right, atomic size. Again, remember, this is all we're focusing all these topics with respect to transition metals, okay? Because transition metals are at the center of our complex ion when we talk about coordination compounds and coordination chemistry, which is the major topic of this section, which is what we're going to start in video number 3, the next video. All right, atomic size or atomic radius trend. Periodic trend is the exact opposite of ionization energy. Size increases from top right down to bottom left. So things like cesium and francium are very large. Barium is also very large. Fluorine and way up in the top right you have the nonmetals. The nonmetals are relatively small. Things like fluorine, sulfur, chlorine, etc. All right. Note, and I've got a few notes I'm making here. Note, number 1, there's a significant increase in size of atomic radius in going from the 3D, that's period 4, right? 3D is period 4. Period 4 is the first time you go all the way right to left across the periodic table. That's when you have the 3D. So going from period 4 down to period 5, in other words, 3D, remember that D's are always one behind the period number? 3D to 4D, there's a significant increase in size of atomic radius. But, and this is bullet point number 2 here, it says 2, there's a minimal increase, if any, in size of atomic radius, or in size of the atom, in going from the 4D to the 5D. In other words, going from period 5 to period 6. So what's happening there? What is the difference in going from period 4 to period 5 with respect to transition metal size versus period 5 to period 6? What's different? Well, what happens in period 4, what happens in period 5, and what happens in period 6? We essentially have 3 periods we need to take a look at here, right? And the minimal increase that we see in going from period 5 to period 6, this major difference is we start to see the lanthanides. The lanthanides show up in period number 6. Okay, that's different than number 1 where we were going from period 4 to period 5. This is called the lanthanide contraction, right? You've got those the F block down there, right? The lanthanide and actinides. And if you can imagine just accordioning them up, jamming them up, and they split themselves in to period 6 and period 7 in the periodic table. So the lanthanide contraction, I've got it underlined with quotes around it. What is it? Well, it says underneath lanthanide contraction, it says the 4F lanthanide orbitals, which are in period 6. Remember, the F are always 2 behind the period number. So period 6, 4F. The 4F lanthanide orbitals in period 6 are buried in the atom's interior. So as the 14 electrons are added to the 4F orbitals, additional electrons don't really affect the atomic size. They're being stuffed into the interior as opposed to the kind of outer, quote unquote, more valence-esque shells. Okay. So although not required for success, it might help you guys if you took the time right now before we started the next video just to review your textbook a little bit. And if I seldom ask you to review a textbook outside of our source of chemistry notes. So it's not required, and it's not even required to be successful, but it might help you to review your textbook for some basic information about the following 3D metals. We're going to be using these 3D metals quite a bit in the videos that lie ahead. So it's kind of important just to kind of have a little bit of a review on them. And we did cover some of them in video number 1 of this section. All right, so I'm going to list these 3D metals. By the way, 3D does not mean they're 3-dimensional. That means they are in period 4, and it's the first row of transition metals. The D block, right, starts in period 4. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. We're going to see a lot of these guys, and they are going to be our central atom in our iron complexes that we're, in our metal complexes that we're going to start to build when we talk about coordination compounds. All right, so that's it for this video. If you like the way I do these handwritten general chemistry notes, I've also got handwritten organic chemistry notes. You can get first semester, second semester, or the full course, and everything is available at chemistrynotes.com, so I'll see you over there. Also, stick around for video number 3 from section 18. That's coming up next. We're finally going to start to talk about the new stuff and the meat of section 18, transition metals and coordination chemistry. All right, so I'll see you then.